Warm welcome. Thank you for joining. Nice to have you here. Grab yourself a notebook, maybe some graph paper, or just a plane, an XY plane with a little bit of space on it. Grab yourself a pen or a pencil. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. So I mentioned you're going to need a plane here. Maybe just make it like -7 to -7 to 7 in the X and Y directions both. I think that should be plenty. You want it to go out about there. Okay, and here we have a particle motion problem, so you should definitely expect that you're going to have to sketch this, especially given my hint that these two particles are going to be moving around, and we have them parametrically defined. Okay, so we have particle A given by this X and Y equation, and we have particle B given by this X and Y equation. Okay, that means that time is controlling both the X and the Y. And then we can begin. So give yourself maybe like 12 or 15 minutes because you're going to have to sketch stuff, so you want to make sure that the direction of motion works, all of these things. Then when you're ready, come back, see how I approach this problem. From 1995. Yeah. The BC exam. Wow. 1995, that's a while. Okay, so let's start. Part A says find the velocity vector for each particle, so both of them, at time t = 3. The velocity. Now the velocity is going to look like what? The velocity is going to look like this. The velocity vector, you can call it. It's going to have x prime as the x coordinate. It's going to have y prime as the y coordinate. So we have to find those derivatives and then plug in 3, and that'll give us the values of the velocity vectors. So let's talk about part A. We can call it VA. That's going to have an x coordinate of 3/2. As you can see, I'm just, whoopsie. That's looking at B. That's my red one. So looking at A, the derivative there is just 1. So I don't even really have to plug in a time for that. And then the y derivative, well, that's going to be y prime, which is 2 times t minus 2 to the 1 power. So it's not so bad there. Okay, and I guess I'll leave it like that, 2t minus 4. Now let's plug in 3, and that's just going to give us a vector of 1, 2. Now if we're talking about velocity of the particle B, that one is going to have 3/2 as its x derivative, its x component of velocity, and its y component of velocity, also 3/2, so nothing to plug in there. Those are our two velocity vectors. Should be pretty straightforward, very easy. They just have you take little baby derivatives, several of them. Part B, set up an integral expression that gives the distance traveled by particle A from t = 0, t = 3. Do not evaluate. So that means you're not going to have to worry about solving this integral. It's probably on a no calculator part. But we do have to set up the integral. And this is specifically for particle A. So how do we determine the distance? That's kind of a really big idea here. Distance. Well, the distance, you might remember, is the integral from the first time to the second time, a to b. But it's the the x derivative squared plus the y derivative squared. Because what we're basically doing is we're looking at the positions, and it's dt. We're looking at the position and the movement as being controlled by two different vectors here, but the overall movement is controlled by these sort of hypotenuses. So the Pythagorean theorem comes in handy here. We're just adding up these small changes in distance. So let's see, from t = 0, to t equals 3. Got it. So those are our limits. Let's go to particle A's equations. I know I'm buzzing you around everywhere. Here's particle A's equations. But what we want to do is we want to write their derivatives inside of an integral expression. So it's going to look something like integral from 0 to 3 square root of the x derivative squared, which is a fixed constant value, it's 1 squared, plus 2t minus 4 squared. And that's dt. Now, how much do they want us to simplify this? I don't really know, but I would say that it's a safe bet to like work this out in case there's any kind of nice simplification that goes on. So this would be 1 plus 4t squared minus 16t and then plus 16. Yeah, I don't think that simplifies to anything obvious, but it still doesn't hurt to check. So plus 17. I don't think that's going to factor to anything particularly nice. Okay, so that would be the total distance. Not too bad. It says do not evaluate, so we're done with that. That also explains why there's 4 parts, because they can't all be really long parts. Part C. Determine the exact time at which the particles collide. That is, oh wow, they really gave you how to do that. They held your hand there. They could have just said that, justify your answer. But they're telling you that it's when the particles, so you're finding a time at the same point at the same time. So what you have to do is you have to say, okay, that means that their x values are equal and their y values are equal. And when you solve for time, you need to make sure that you're getting the same exact time. Just because they cross the same x value doesn't mean they're crossing each other. What if one of the particles is doing this, and at a certain time it has the same x value as the other particle that's doing like this? So at the same time, they might have the same x value, but that doesn't mean they're colliding. They have to have the same x value and the same y value, and it has to happen at the same time. So it'd be like t equals c for this, and it would also be like t equals c for the other curve. Okay, that looks kind of cool, but I'm gonna eliminate that. All right, so let's start with the one that's going to be more obvious. I don't want to set the y's equal to each other first. Why not? This is a little bit of a strategy tip, because I'm probably going to get 2 solutions since there's this quadratic thing. I'd rather work with the 2 x values because I'm not going to get 2 different solutions. I'm going to get a single time, and then I can plug the time in to the y's and just see if it gives me the same y. All right, that's the strategy. So let's set the x from particle A, which is t minus 2. Let's set that equal to the x coordinate for particle B, which is 3/2 t, what was it, minus 4? I should have paid attention, yeah. Okay, so let's just move this is basic algebra. I mean, I'm not even really gonna explain too much about what we're doing. It is 1/2 t equals positive 2, multiply both sides by 2. Oops, 4 equals 2, yeah, that makes sense. T equals 4, so that's when the x values are equal. Now, because it doesn't say if they collide and it says when they collide, I mean, I guess we already sort of know that they will be colliding, but we still have to check. So let's plug this into the y equation. So we're going to basically say, for particle A first, I guess. What was it? T minus 2 squared. 4 minus 2 squared. That's just 2 squared 4. So that's the y of A. And then for B, we have 3/2 t minus 2. So 3/2 4 minus 2. Yep. Fair enough. That equals yb. So we can confirm that time t equals 4, the y values are also equal. Nice. And it says what? It says the time. That's the answer they're looking for. The point is sort of more scattered, so if they wanted to point, we would have to organize that a little bit more nicely. And then part D, of course. In the viewing window provided, sketch the paths of particles A and B from t equals 0 until they collide. So let's say t equals 0. You could eliminate the parameter here if you'd like. It's not a bad idea. So if you eliminate the parameter for this, obviously that t minus 2 is what x is equal to. So that's just the equation y equals x squared. Pretty freaking simple to graph that, is it not? And then for B, kind of a similar thing. It's not too hard to figure out the parameter because this is 3/2 t minus 4. This is 3/2 t minus 2, which is simply 2 more than the x. So really we have y equals x plus 2 for particle B. It's not too hard to do that, and it saves time rather than trying to like just plug in t times like t values. You might pick up on the pattern, but by that point you're going to have wasted a lot of time. So maybe that's what you did when you tried to solve this problem, which, I mean, it works if you plug the points in correctly. It's just a lot more work to do. So choose wisely. Let's see, starting at t equals 0, the red one's going to be right here at 2, and the purple one is going to be right here at 0, 0. So at time t equals 1, we have 1, 1, and we have 1, 3, because that one's going in a straight line. That seems strange that it would take that long for them to meet. T equals 4? Oh, that's the part where I'm messing up at, because got it. It is good to keep that parametric definition, because when t, that's the curve. These are the curves. That's accurate. But when t equals 0, we're pretty far back. Yeah, I was noticing they're going to cross really soon, and it's because our first point for t equals 0 is x equals -2 and y equals 4. And let's see, for the particle B, x equals -4 and y equals -2. Got it. X equals -4, y equals -2. There we go. Right. And so if we graph this in time, of course, it's going to look like they're supposed to cross more than once. But because of the timing, they don't cross at the exact same time. Let's see, t equals 3. Actually, I think I went a little bit too far. Because if t equals 3, then we're going to end up at 1, 1. Yep, plug in 3 for t. Get 1, 1. And yeah, they do not collide here. Their paths cross, but they don't collide in time. And let's see, how far is this line going to go then? This line is only going to go maybe like, if I plug in 3, I get 9/2 minus 2, which is like 5/2. Okay, so it will have just crossed, barely. Something like that. There's the direction. That indicates the direction from left to right on both of these. Okay, indicate direction of each particle along its path. There we go. Oh, until they collide. Whoops, I thought it was until t equals 3. Until they collide. Gotta keep reading that question better. So they are going to collide at this spot. Does that look kind of bad? Let's see, what's the point that they're crossing at? It's going to be at 2, 4. Yeah, that does look pretty crappy. Let me do this again, I apologize. So if we start at t equals 0, that's really the key of where we want to start off at. Let's make it go through there, and then it goes through there, and then it goes through there. And then we have the purple graph, which starts at -2, 4, goes through there, but they don't collide. You'll see that at 1 second, that's where this graph is at. But the other line is not quite there yet. And bam. And then indicating the direction, again, we go from left to right on both of these graphs. All right, that looks better. Yikes. Hopefully that didn't take you as long as it took me to graph. And it's a good thing we didn't have to evaluate this integral. I guess we would have just used the calculator anyways. But that is what you can expect from a problem like this, is maybe having to eliminate the parameter, or in some cases where you don't have to eliminate a parameter, usually it's a sine and cosine graph. And so you can just use methods that you understand about period and sine and cosine in order to interpret the overall graph. We didn't have to talk about acceleration. We just got to velocity, but that still required a derivative. However, we didn't have to find any maximums or minimums. It was mostly about finding out whether these two particles collide or not, and then drawing the path. All right, well, that's enough blab out of me. I'll catch you guys next time in the voice.